In the final exercise of selected set 4, we meet Lotte. And Lotte has an initial wealth of 400, but she faces a risk. With probability 0.1, she will enter a bad state of the world, which in her case means that she will lose 300. And with probability 0.9, the good state of the world will happen and she will not lose anything. So think of this as the probability of losing your phone, for example, or that the screen of your phone breaks, or all kind of bad things that may happen to someone. So she faces the lottery curly L 0.1 equal to minus 300, 0.9 equal to 0, and she has a utility of wealth function which is quite simple. It's just the square root of her wealth. And in this exercise we will also do a bit of drawing, and we can see the initial wealth level and initial situation of Lotte here. And it's this point where if the good state of the world materializes, nothing will happen and her wealth will be 400. If the bad state of the world will occur, then her final wealth will be 100. And there are tons of questions in this exercise, so they run all the way to F, but we will just start with A in order to not get lost. So this is a summary of the information in the description of the exercise, and in exercise A, the task is very easy. We need to compute Lotte's expected utility if she involuntarily has to face the risk. So this is straightforward. With probability 9 over 10, nothing will happen. Her final wealth will be 400. In that case, her utility will be the square root of 400. With probability 1 over 10, she will lose 300. Final wealth will be 100. So final utility will be the square root of 100, and the expected utility therefore is equal to 19. And then again we can continue with question B. So what is Lotte's certainty equivalent to facing this lottery? So what is the amount of wealth she is willing to give up in order not to face the lottery, in order to not to be exposed to the risk of, for example, losing her phone? And then how much is she prepared to give up in excess of the expected loss of facing the lottery? So two questions in one, and let's start with the first. So for the certainty equivalent, it needs to hold that Lotte will be indifferent between facing the lottery and not facing the lottery. So, and if she faces the lottery, we computed in A that her expected utility will be equal to 19. So if we could give Lotte certainty in a certain amount of wealth that would make her indifferent between facing the lottery or not, then we would have found the amount of wealth, the certainty equivalent that makes her indifferent between the two. So this is the expression that we want to solve using the square root utility function. We get this expression over here, and the certainty equivalent is equal to 361. So in this case, Lotte is indifferent between facing the lottery and having for sure a final wealth of 361. So that's the first question in question B. The second question is, okay, how much is she prepared to give up in excess of the expected loss of facing the lottery? Now she's willing to give up 39 because she starts out with a wealth of 400. She's okay if instead of facing the lottery she ends up with, for certain, with a wealth of 361. The difference between the two is 39, and that's the amount she is at most willing to prepare in order to get rid of the risk. However, the expected loss of facing the lottery is smaller because, well, the loss is equal to 300. The probability that happens is 1 over 10. So the expected loss is equal to 30. So to answer the second question that's posed here, the amount that she's willing to give up in excess of the expected loss is equal to the difference between 39 and 30. So she's willing to pay an additional 9. And then we can continue with question C. So now suppose that Lotte's initial wealth is not 400, but that she's richer. So her initial wealth is 900. And then again compute the certainty equivalent. So what amount will now make her indifferent between facing the lottery or not, and also compare it to the expected loss. And how does the difference change with the initial wealth, and what does it tell you about Lotte's absolute risk aversion? Again, number of questions in one sub-question, but none of them is very complicated. So if the initial wealth is 900, the expected utility when facing the lottery and being exposed to the risk is equal to 90%, we end up with 900, 10% we end up with 600. So the expected utility of being exposed to the lottery is about 29.45. So what amount of wealth makes her indifferent between facing the lottery or not? So what is the certainty equivalent? Again, we equate the square root of the certainty equivalent to 29.45, and we end up with a number of about 867.27. And this implies that she's willing now to give up 32.73 of her initial wealth in order to avoid the risk. And as you can see, if you compare it to question B, there she was willing to pay up to 39 in order to get rid of the lottery, and now she's willing only to pay up to 32.73. So her willingness to pay to not facing the risk has reduced. So, and what does it indicate? It indicates that Lotte's absolute risk aversion is decreasing with her level of wealth. So, quite a number of questions in this sub-question, but as you can see from the solutions, the answers are relatively small and straightforward. Then question D is something somewhat more complicated. So obtain the slope of the fair odds line. And then you get a hint. The fair odds line corresponds to the case where insurance is sold at fair, perfectly competitive prices. So an insurance company that offers you to insure against the risk will not make any positive expected profits from doing so. And then prove by derivation that the slope of the indifference curve passing through the intersection of the certainty line and the fair odds line equals the slope of the fair odds line. And now, this is a more complicated thing to do because you might not find it straightforward what you are asked to do. So let's do it together. So suppose that there is fair insurance. Now we know that the risk to which Lotte is exposed, the expected loss is equal to 30. So 10% chance of losing 300. So the expected loss is 30. So in a perfectly competitive insurance industry where insurance is offered at fair prices, the insurance company should also offer you to be insured against this loss at a cost of 30. Because the expected loss is 30, the insurance company should not make a profit in expectation. So also the premium that the insurance company should receive from you is equal to 30. And with a premium of 30, the insurance company would, in expected value, even out. So it means that, and if you have insurance, it and full insurance, it means that whatever happens, good state of the world, you keep your phone, or bad state of the world, you lose your phone, your final wealth will be the same. So you're no longer exposed to this uncertainty. Both in the bad state of the world and the good state of the world, you will end up with 370. And the 370 is just your initial 400 minus the fair premium that you paid for the insurance. Now, graphically, this looks as follows. We start out from here. Now we can buy fair insurance. So all the full insurance lines policies are on the certainty line. So the certainty line, by definition, gives you the same payoff in the good state of the world and the bad state of the world. And the particular point that we consider here is point E, where Lotte receives 370, both in the good and the bad state of the world. So she starts out here, where she is exposed to the risk, and she is offered to buy full insurance, where she will end up here, and she can also decide to only partly insure, which would make her end up somewhere here. And what we now need to prove is that the slope of this thing is equal to -9, and that at point E, the indifference curve of Lotte that runs through point E is tangent to the fair price line. Now, how to do it? The slope of the fair odds line is identical to -9. So you can see it as follows. I need to give up 30 in the good state of the world. I move from 400 to 307 in order to get 270 more in the bad state of the world. So not 100, but also 370. So that's the slope. So this is what I divide in order to get the slope of the function. And you can see that -9 is exactly the ratio between the probability of being in the good state of the world, which is 0.9, and the probability of being in the bad state of the world, which is equal to 0.1. So the slope is equal to -9. And this is what Lotte is offered when the insurance industry is perfectly competitive. Now, other way to get to this slope is also if you answer the question, if I give up 1 in case of the good state of the world occurs, what is the fair amount of X that I should receive conditional on the bad state of the world occurring? And then you should realize, well, the actual value of receiving 1 in the good state of the world is 1 times the probability that the good state of the world happens. And the cost of giving up this value should be equal to the expected benefit that you would get of receiving an additional X in case the bad state of the world happens. So the equation should be like this. The value of giving up 1 in the good state of the world should be identical to the expected benefit that I get times the probability that the bad state of the world occurs. Okay, so and that leads to this expression over here, which gives you also this ratio. And for example, if the bad state of the world would occur with probability 0, yeah, then you would need an infinite amount of money, and it would not even be sufficient in order to compensate you for giving up something in the good state of the world, because the bad state of the world will never happen. And the general fair odds line is written as can be written as this expression over here, where we add 3,700 because the initial point of Lotte needs to be included there as well. Okay, so that completes the first part of exercise D. And now we need also to look at Lotte indifference curve. So her expected utility function is identical to 0.9 in the good state of the world plus 0.1 utility in the bad state of the world. And now we take the partial derivatives with respect to WB and WG. And we get two expressions. So if we take the derivative with respect to WG, then it's 0.9 times the derivative of our utility with respect to WG, and the same for the bad state of the world. And what we now actually do is we look at the marginal rate of substitution. So we know that the marginal utility of an extra banana divided by the marginal utility of an extra coconut. In this case, we consider a payoff of 1 in the good state of the world as a different good as a payoff of 1 in the bad state of the world. So our two goods are now what we get in the good state of the world versus what we get in the bad state of the world. So the marginal rate of substitution in this case is the derivative of being in the good state of the world divided by the derivative of being in the bad state of the world, and then the minus sign because these things are positive and the marginal rate of substitution is negative. And we can just plug in for these expressions the things that we have over here, and we get minus 9 times these derivatives. And now, and this is a key point, at the certainty line, it's always the case that the wealth in the bad state of the world is identical to the wealth in the good state of the world, which means that the marginal utility of adding some wealth in the good state of the world at that particular point is identical to the increase in utility that we would receive if we would increase the payoff in the bad state of the world, because the initial wealth levels in both of the states of the world are identical. So also the marginal utility of additional wealth is identical at those points. Which means that these two derivatives are identical to each other and therefore cancel out, and we get the marginal rate of substitution at the certainty line at point E is identical to minus 9. And that completes exercise D. Then in exercise E, assume that Lotte can buy insurance policy for any sum at a fair premium rate, which means that, okay, she can pay a premium equal to the chance that the bad state of the world happens times the amount X that she wants to insure. If she pays that amount, then in the bad state of the world, she will receive a payment equal to X. So this is a situation where Lotte has an initial wealth of say 1,000, and then she can decide, okay, if my house catches fire, then I will lose my wealth, my entire wealth, and now I can decide on which part of my house to insure. So I can take full insurance, so I can set X equal to 1,000. In that case, I will pay a premium. Well, if pi b is equal to 10, I will pay a premium of 10. If my house burns down, I will get full coverage and I get 1,000. I could also decide only to insure against for half of my house. In that case, my premium will be 0.10 times 500, so it will be 50. My premium will be smaller, but if my house burns down, well, I will lose a value of 1,000 and the insurance company will only pay out 500. And the question is how much of my initial wealth, how much of my house I will insure. And you should derive that buying full insurance, so just covering the entire house, will be the best thing for Lotte to do. Now, the expected utility of Lotte is, okay, in the good state of the world, I will still have my initial wealth, but if I bought insurance for a sum X, I will have paid a premium equal to 1.1 times X. So that's the amount that I will lose, also in the good state of the world. And if the bad state of the world happens, yeah, then I will face a loss of 300, but part of it has been insured. So in that case, I will get X from the insurance company, but I also have paid 0.1 times X in order to get the insurance policy. So net, I will get 0.9 times X. So this is crucial to get this. And once you have this, it's straightforward. So you can differentiate the expected utility again with respect to X. And doing so, we get these expressions over here. And we can again bring this to the right hand side, take squares, simplify, and finally you will get that X needs to be equal to 300. Now, Lotte initially faces a loss of 300. Now she decides to buy an insurance policy for a sum X equal to 300, which means that she buys full insurance. The premium that she will pay, capital Pi, will be equal 0.1 times the amount that she insures, which is 300. So her premium will be equal to 30. And then in both states of the world, her wealth will be 370. In the good state of the world, 400 minus the premium she paid. In the bad state of the world, 100 minus the premium of 30 that she paid, plus the amount of 400 or 300 that the insurance company pays out, also has her arrive at a final utility or final wealth of 370. Now, the instructive part of the exercise is that in question E, insurance is offered at a fair premium rate. So for any loss of 1 unit, you only need to pay a premium of 10 cents. But in question F, the insurance companies, they offer less good insurance policies. So in question F, the premium rate is 0.12. So the bad state of the world will still happen with probability 10%. But if you want to insure a sum of €1, now you don't need to pay 10 cents, but you need to pay 12 cents. And again, you need to compute for this premium which sum Lotte will insure. And we need to also depict it in a figure as a point F. The computation is the same. So with a premium of 12, the good state of the world will still happen with probability 90%. In that case, she will end up with a final wealth of 400 minus the premium that she paid. And the premium will be identical to 0.12 times the amount that she insured. And if the bad state of the world happens, well, she will also pay this premium, but she will also receive X from the insurance company. So net, she will get 0.88X on top of her final wealth of 100, because well, she loses the 300 of her initial wealth. Again, this is a crucial expression because now for finding the optimal X, we take the first order condition with respect to X. So, and this is the derivation. So we take the derivative, we get these two expressions. We multiply everything by 1000 in order to make things more tractable. Gives you these expressions over here. You take the power of 2 on the left hand side and also on the right hand side to get rid of the square roots. Well, taking the power, this to the power 2, you get this expression, which simplifies to 729 over 484. And now we need to solve for X. this expression, so we bring this to the left hand side, we multiply by 729, we get this expression over here. We bring this to the numerator of the right hand side and multiply with 400 minus 0.12x. We get this expression over here. Then we further simplify and we find that now with the less attractive insurance policies, Lotte will not insure the full amount of 300, but she will only insure an amount of 172. So she will not buy full coverage, and we can depict it as point F, because now in the good state of the world she will end up with 400, but she needs to pay an insurance premium. Well, she decides to insure an amount of 172. The premium that she will pay is 0.12, that amount, so she will end up with 317.18. And in the bad state of the world, she will also pay that premium. Yeah, so there's a mistake over here. So forget about this thing. In the bad state of the world, she will also pay the premium, but the bad state of the world means that she will lose 300, but she's partly insured, so she will not lose the entire 100 because 172 will be paid to her by the insurance company, so her net loss will be 300 minus that amount. And if you compute this, then her final wealth will be 251 times 83. And we can depict this point in the graph. So the insurance policies are now not fair. You pay a higher premium, which means that the opportunities line, the price line is a little bit less steep. So it's like this line over here. In order to get coverage in the bad state of the world, you now need to give up more in the good state of the world. And the optimal point that Lotte will choose will be the point F over here. And this completes exercise number 4.